coming from the last video where we introduced Bodhi plots and we looked at a fairly easy example where we had h equal to 1 plus j omega divided by a. We saw that Bodhi plots can be fairly nice at approximating the frequency response, but sometimes the functions that we get for h aren't nice at all, and sometimes it gets really complex. So for that, we're going to consider an example where we have h given by k times 1 plus s divided by s1 times 1 plus s divided by s2, where simply recall that s is equal to j omega. So we just make a substitution for s equal to j omega, and then we recall our relation to find the dB value of h. So from this, we're going to use the property for logs, where we have log of a times b times c, and that can be expressed as log of a plus log of b plus log of c. And that allows us to expand that equation above into 3 terms, where we simply have the first term, the middle term, and the last term. And then we can also use the property where if we have log of a raised to the b, we can pull out that b to the front and have b times log of a. So we can simplify just a little bit more to arrive at this. And the question is, what do we do from this? This still seems pretty complex, but the answer is fairly straightforward. We take each term and we evaluate it, and we sum them all together. So the divide and conquer method, that's what we're going to use. And if we look at that first term, we simply know that no matter the value of omega, we're always going to get 20 times log 10 k. So it's a constant for all omegas. Looking at the second term, we're simply going to have 10 log 10, 1 plus omega divided by s1, that quantity squared. And we know from the last video at omega much less than s1, our output is 0. And we know that for omega much greater than s1, we have a positive 20 dB per decade increase. And the third term looks a lot like the middle term. So we get a similar nature where we get a 0 for omega much less than s2 and a 20 dB per decade increase for omega much greater than s2. So what we can do, we can take all 3 of these and we can plot them independently like we did here on the left. So if we sum all of these terms up together, you can see that up to S1, really only the red part is contributing. But after S1, we have the red and the blue contributing, where we have a 20 dB per decade increase. And then once we get to S2, we have all 3 of the plots contributing. And now we have another 20 dB per decade increase from the green function. So that gets us to a 40 dB per decade increase after S2. And we could go ahead and see what the values are at S1 and S2 for both of these plots. And then this approximation might smooth out around these sharp corners. But in essence, that's how we look at complex Bodhi plots. We try to fit them into forms that we are comfortable with, and then divide and conquer, add them all back up, and plot them. So we know that if we have h equal to 1 plus s divided by a, we get this 20 dB per decade increase. But if we look at h being equal to a divided by a plus s, we get this relation for h dB, which we can simplify like this here on the right. And we can take this -1 and move it out front because it's just raised to a power. And if we do that and clean up the terms a little bit, we simply get this bottom term here, where you can see that this looks very familiar to this function up here, except we get this negative sign that appears. So what this is going to lead to is simply a -20 dB per decade decrease. So rather than increasing like we had up here, we'd have a decrease, and that would be -20 dB per decade. And if we can fit the transfer function h into either of these forms, Bodhi plots are pretty easy to work with. But if we can't do that, there's another form that we try to force. And that form is given right here, where h is equal to 1 plus 2 times zeta times the quantity of s divided by omega naught times the quantity of s divided by omega naught squared. And while this seems pretty complex to evaluate, you'll see that this is quite easy to work with. And what this polynomial represents is a resonance circuit. And the zeta term is what we call the damping factor, and it is a value between 0 and 1. And if zeta is greater than 1, we can break it up into a form like this, and we get our comfortable to work with functions that we've been previously looking at. So if we say that h is equal to that polynomial, we simply want to look at the dB value of h. So we have 20 log 10 times the magnitude of h. And we don't really need to evaluate the magnitude per se, because we're going to look at two conditions again. One for omega much less than omega naught. So we can see that this middle term and this last term are negligible, and we get 20 log 10 times 1, and we know that that simply equal to 0. Now we can look at the case for omega much greater than omega naught. We're going to say that this last term is the dominating factor. So we can make the approximation that we have 20 log 10 omega divided by omega naught squared, and then we get this minus sign. But because it's the magnitude, we can simplify this as 40 log 10, and that actually gives us a 40 dB per decade increase. And then there is one last term which we do need to consider, and that is when omega is equal to omega naught. So from this, you actually get this first term and this last term canceling out. And this is where we need to know what that zeta value is. So if we go ahead and plot all of these conditions, what we get is the following, where around omega naught, you can see that you have this transition from 0 to this 40 dB per decade increase. But then depending on what zeta is, you get this nature of this dipping. And if zeta is equal to 1, you can see that you get kind of the smooth tendency that we had previously. Now, combining everything, we want to consider function h being equal to all of these terms here. And the first thing that we're going to do is try to fit the form that we derived at above. So we know that we want some part of h to look like this. So we're going to divide by 10 to the 4th, or 10,000, and that's going to give us this transfer function. And the reason doing that was so that we could get a 1 right here. Now, from this, just making substitutions, we can say that 2 times zeta times that quantity of s divided by omega naught is going to be equal to 0.002s. We can say that s squared divided by omega naught squared, that's going to be equal to 0.0001 s squared. And from this, we can simply say that omega naught is equal to 100. Now, once we know that omega naught is equal to 100, we can plug it in here, and that allows us to find our zeta value, where zeta is simply equal to 0.1. Now, if we take that transfer function and we have our polynomial form that we desire here, and then we have some stuff going on here in the numerator and then this other term in the denominator, we can simply take the dB value of h. Again, using the properties of logs, we can break that up into 4 terms. So from all of these terms, what we get is that this first term is simply a constant. This second term is a little bit skewed from what we looked at above, but we can look at the values of omega. We can see that we have this 20 dB per decade increase. And then instead of a 0, we just keep going down. For the third term, because of this minus sign right here, we had a minus 20 dB per decade decrease, and that occurred at omega equal to 1. And then this last term here is flipped from what we had above, where again, minus sign, so we have minus 40 dB per decade decrease at omega equal to 100. So our plot looks like this, and because zeta was equal to 0.1, we get that dipping, or in this case, it's flipped. So what we can do, we can take all of these functions, simply add them up together, and this is what our total frequency response of that transfer function. Now, like it was brought up in the first part of this video, not all transfer functions are easy to work with or easy to force into forms that are easy to work with. Sometimes you just get a really nasty transfer function that you have to plug into MATLAB or something similar and actually see the frequency response. That's just the way it can be sometimes. But if you can force it into functions, you can see the behavior pretty quickly and see what's going on.